Hello, and welcome to Controllers Tech. Today, we are beginning a brand new mini-series focused on STM32 IoT projects using the ESP8266 Wi-Fi transceiver module. In this series, we will explore step-by-step how to connect the STM32 to a Wi-Fi network using the ESP8266, how to send sensor data to a cloud server, and how to control STM32 GPIOs directly from a web dashboard. Along the way, we will also implement the MQTT protocol, and towards the end, we will even try out STM32 over-the-air (OTA) firmware updates through the ESP8266. This is going to be a very exciting set of videos spread across the next couple of months, and it will give you a strong foundation in building IoT applications with STM32. In today's first video of the series, we will start with the basics. We will look at how to configure STM32 Cube, how to make the hardware connection between STM32 and ESP8266, and finally, how to use simple commands to connect the ESP8266 to a Wi-Fi network. For this entire series, I will be working with the STM32F446 development board from WiFi Studio. If you're based in India, you can also purchase this board directly from shop.controllerstech.com. On the Wi-Fi side, I will be using the ESP8266-01 serial Wi-Fi module. This module is quite compact, but it comes with multiple pins, which can make direct connections to the development board a bit inconvenient. To solve this issue and simplify the setup, I'll be using an ESP8266 adapter. This adapter reduces the number of pins from 8 down to just 4, leaving only TX, RX, VCC, and ground. This makes it much easier and cleaner to connect the module with the development board. All the links to the components I am using in this video are provided in the article mentioned in the description below. If you would like to support the channel, you can do so by purchasing through these affiliate links. It really helps us continue making more content like this. Before we begin working on the STM32 project, the first step is to make sure that our ESP8266 Wi-Fi module is responding correctly to AT commands. To test this, we will connect the ESP8266 to any USB to TTL converter, which will then be connected to the computer. The wiring is very straightforward. Connect the pins in a cross fashion. The TX pin of the ESP8266 goes to the RX pin of the converter, and the RX pin goes to the TX pin of the converter. If you're using the ESP01 adapter, you should provide it with a 5 volts power supply, since the adapter already has an onboard voltage regulator that steps it down to 3.3 volts, which is the operating voltage of the ESP8266. However, if you're connecting directly to the ESP8266 module without the adapter, make sure you supply 3.3 volts only, otherwise you may damage the module. Once the connections are ready, open any serial terminal software and select the correct USB TL port. Now, the ESP8266 modules usually have different baud rates. I'm not sure which baud rate this one is set to, but by default, many modules are programmed with 9600 bps, so we will start by trying that. When sending AT commands, remember they must be followed by both carriage return and line feed characters. Some serial terminal programs allow you to automatically add this tail, but if yours doesn't, you can manually include it in the command itself. Let's begin by sending a simple AT command. The command was transmitted successfully. The send count shows 4 bytes, 2 for the command and 2 for the tail. However, we did not receive any response from the module. At this stage, the first thing you should do is check your wiring and the power supply to ensure everything is correct. In my case, the connections are fine, so I'll try changing the baud rate to 38,400 bps and send the command again. This time, we receive some data back. That means the module is alive, but clearly the baud rate is not yet correct. Next, I'll try another common baud rate, 57,600 bps. After sending the AT command at this rate, we received 6 bytes, but still not the proper response we were expecting. Now, let's switch the baud rate to 115,200 bps and test again. This time, we received the correct response from the ESP module. It replied with OK for the AT command. That confirms the module is configured to operate at 115,200 bps. It's possible that I had reconfigured this in one of my earlier projects, since most ESP8266 modules originally come preset to 9,600 bps. With the baud rate confirmed, let's try out a few more AT commands. AT plus GM is used to check the firmware version. As you can see, the ESP module responds with its AT version and SDK version details. Notice that every valid response ends with OK. This is important because later, in our STM32 code, we can use that as a marker to confirm successful command execution. AT plus CW mode is used to check the current Wi-Fi mode of the ESP module. The response shows mode 1, which means the module is set to station mode, allowing it to connect to an existing Wi-Fi network. AT plus reset can be used to restart the module. As you can see, the ESP module reboots successfully. Now, in my case, the Wi-Fi is already connected. That's because during a previous test, I configured the network credentials, and the ESP8266 stored them in its internal flash memory. Because of that, it automatically reconnects during boot. So everything looks good. The module is working, responding properly to AT commands, and is ready to be used in our STM32 IoT project. I have already written the library files that will handle the processing of AT commands, and we'll be using them in the project later. You can download these library files from the article linked in the description of this video. Now, let's move to the STM32 Cube IDE and create a new project. As mentioned earlier, I will be working with the STM32F446RE development board. Let's give the project a suitable name, and then click Finish to create it. We will begin by setting up the clock configuration. For this project, I am selecting the internal oscillator, and I'll configure the system to run at its maximum frequency of 180 MHz. Next, let's configure the UART that will be used to communicate with the ESP module. I am assigning UART4 for this purpose. The pins PA0 and PA1 will serve as UART4TX and RX respectively. From our earlier test, we already know that the ESP module is communicating at a baud rate of 115,200, so we will configure UART4 with the same baud rate. Leave the rest of the UART settings at their default values. In addition to this, we need one more UART to view user interactions and to log debugging information. For this, I will use UART1. The pins PA9 and PA10 will act as UART1TX and RX. I will keep the baud rate for UART1 at 115,200 as well. That's all the configuration required in CubeMX for now. I will show the actual hardware connections in just a bit. For now, click Save to generate the project. The first thing we'll do inside the project is to copy the library files. Copy the C source file into the project source directory and the header file into the include directory. Let's take a closer look at the ESP8266 STM32 header file. Here, we need to specify which UART is being used for the ESP module. If you're using a different UART than what I've shown, you can configure it here. I recommend keeping the user logs enabled because they display important information about the ongoing processes. If you encounter errors, you can then enable the debug logs, which will print detailed step-by-step messages showing exactly what led to the error. This makes troubleshooting much easier. Currently, the library provides 3 global functions. ESP_NIT. This initializes the ESP8266 module. ESP_Connect Wi-Fi. This connects the module to a Wi-Fi network and retrieves its IP address. The parameters for this function are SSID and password of the Wi-Fi access point. An IP buffer to store the assigned IP address, and the buffer length, which defines the maximum size of that IP buffer. ESP_getConnection. This function allows us to check and retrieve the current connection status of the ESP8266. Now, let's go through how these functions are written inside the source file. We'll begin with the initialization function. Inside this function, the first step is to restart the ESP module by sending the AT+reset command. Just like we did earlier in the serial terminal, this command must end with a carriage return and line feed. After the command is sent, the module immediately acknowledges it with an OK response. However, the restart process itself continues for a few seconds in the background. To allow the module enough time to reboot properly, we add a delay of about 5 seconds after sending this command. If you do not want to restart the module every time, you can simply skip this part of the initialization function. In that case, just add a small delay at the very beginning of the function. This short pause ensures that the ESP8266 does not receive commands while the STM32 code is still flashing. Once the restart is handled, we can begin the actual initialization by sending the basic AT command. Here, we expect the module to respond with OK, which confirms that communication is working. If the response is valid, we then proceed to the next step. The next command we send is ATE0, which disables command echoing. Again, we wait for the OK response. Once this response is received, we consider the module successfully initialized. The second important function is ESP_connect Wi-Fi, which connects the ESP8266 to a known Wi-Fi network. The process starts by setting the module to station mode using the command AT+CW mode =1. As always, we wait for the OK response to confirm that the command was accepted. Next, we send the command AT+CWJP along with the SSID and password of the Wi-Fi network as parameters. The module now attempts to connect to the access point. Since this process takes a little longer, we provide a timeout of 10 seconds. If the credentials are correct, the ESP8266 will respond with Wi-Fi connected. In general, the timeout values vary depending on the command being sent. I have set the default timeout to 2 seconds, but you can adjust this based on your needs. Once the module is connected to the Wi-Fi, we call a static function called getIP to retrieve the module's IP address. Inside the getIP function, we send the AT+C IFS or command and wait for the response. Since my module is already connected to Wi-Fi, let's try this command directly. As you can see, the module responds with its IP address, MAC address, and an OK at the end. In this response, the IP address is associated with the label station IP. So in our code, we search for the keyword STAIP in the incoming buffer. Once we find it, we extract the IP address that appears immediately after it and store it for use in the project. Finally, let's look at how the send command function works, since this function is central to all communication. Inside send command, the command string is first transmitted to the ESP8266. After that, we begin reading the incoming data from the module 1 character at a time and store it in the RX buffer. While capturing this data, the function continuously checks if the expected acknowledgement string, for example, OK, appears in the buffer. If the acknowledgement is found, the function returns success. And throughout this process, if debug logs are enabled, they will print detailed messages at each step of the function. This makes it very easy to follow what's happening inside the code. Now, let's move on and write the main file. First, include the ESP8266 STM32 header file. Next, we will define a custom write function. This function will route the printf output to UART1 so that all log messages can be displayed on the serial console. Inside the main function, the first step is to call the ESP_init function to initialize the ESP8266 module. If initialization fails, we will print an error message on the console and call the error handler function to stop further execution. Once the module is initialized successfully, we call the ESP connect Wi-Fi function and pass the network SSID and password as parameters. I am connecting the ESP8266 to my home Wi-Fi network, which is also the same network that my computer is connected to. The IP address assigned to the module will be stored inside a buffer, so we need to define this buffer first. To make it reusable later in the series, we will define the buffer globally. If the connection function fails, once again, an error log will be printed and the error handler will be called. Now, let's build the project. The code compiles without any errors, which means we are ready to flash it to the development board. Before flashing, let's double-check the hardware connections. The RX pin from the ESP adapter is connected to PA0, UART4TX. The TX pin from the adapter is connected to PA1, UART4RX. The ESP adapter is powered with 5V from the STM32 board itself. Make sure the USB cable is plugged into the development board, since the ST-Link V2 provides only 3.3V for the board. If you're using an external 5V supply for the ESP adapter, ensure that the ground of the external supply is properly connected to the STM32 board's ground. For debugging logs, the PA9 UART1TX pin is connected to the RX pin of the ST232 USB to serial adapter. Since we only need to send logs to the console, connecting just the TX pin is sufficient. With everything connected, let's flash the project to the board. Now, open the serial terminal on your computer, select the correct port, and set the baud rate to 115,200. Here you can see the sequence of events. The ESP module begins initialization. Once initialized, it switches to station mode. It then connects to the Wi-Fi network. Finally, the module retrieves and displays its IP address. Everything worked as expected. The process went smoothly from initialization to Wi-Fi connection and finally obtaining the IP address. At this point, our STM32 board with ESP8266 is ready to handle network-based protocols. If you encounter errors in the user logs, you can always enable the debug logs for a more detailed breakdown. Let me show you an example. With debug logs enabled, you can see every step clearly. It logs which command was sent, whether the expected response was received, and even displays the entire buffer received after each command. So, that completes this part of the tutorial. I hope this video helps you successfully connect your STM32 to the network using the ESP8266 module. This is just the beginning. We will continue building on this series in the upcoming videos. In the next video, we will focus on logging sensor data to a cloud server. I will use the BME280 sensor to read temperature, pressure, and humidity, and then log that data to the ThingSpeak cloud platform. After that, we will move on to exploring network protocols like the MQTT client. That's it for this video. You can download the full project from the link provided in the description. If you have any questions, or if there is a specific topic you would like me to cover in this series, feel free to leave a comment. Keep watching, and have a great day ahead.